Out there, beyond the soft blue cradle of Earth, lies a stage so vast that even our wildest imaginations stumble in its darkness. The universe doesn't just stretch, it yawns into something unknowable, like a shadow that never ends. And inside that shadow, cosmic phenomena unfold that feel less like facts and more like riddles whispered by reality itself. We think we've mapped the rules with neat equations and laws carved into textbooks. But the universe is far older, far stranger, and far less concerned with our understanding than we dare admit. Every star, every galaxy, every flicker of light across billions of light years carries a story that science can't fully decode. A story that doesn't care if we ever find the ending. Consider the black holes, those silent monsters that swallow everything, even the light that dares to approach. What happens beyond that event horizon? We say singularity, as if naming it answers the question. But it's no answer at all, only a word standing in for the void of our comprehension. Then there's dark matter and dark energy, those unseen forces making up most of the universe, sculpting its shape and stretching its edges like invisible hands. We don't know what they are. We only know they must exist, or everything we believe about reality collapses. The cosmos is a hall of mirrors, reflecting truths we cannot hold. A star may collapse into itself and vanish from our sight, but its gravity continues to shape space, as if it's both there and not there. Light, traveling for billions of years, may show us galaxies that no longer exist, their depths hidden by the sheer time it takes for their glow to reach us. Time itself is different out there, bending and stretching around mass and speed, making yesterday and tomorrow blur into something unrecognizable. This is not a universe that likes to be understood. It's a riddle we're forced to live inside, a paradox so grand that even our finest instruments barely scratch its surface. In this journey, we'll dive into the most unexplainable cosmic phenomena science has dared to confront those phenomena that hum with mystery, taunting our curiosity with secrets too vast, too strange, and too beautiful to fully grasp. Welcome to the edge of the unknown, where every question only breeds more questions. Imagine a beam of light, the simplest messenger of the universe, traveling in a straight line. It moves faster than anything we know, unshaken by the passage of time or distance. But in the deep corners of space, near the jaws of a black hole, or the folds of extreme gravity, this simple beam begins to behave like a dream folding in on itself. It bends, it twists. Sometimes it loops so severely that it appears to return to the very place it came from. This is not an illusion. It's the universe itself warping the path of reality, and light simply follows. This is the paradox of light that bends back, a reminder that even the fastest traveler we know can be trapped, turned, and confused by the cosmos dot. To understand this paradox, we must first admit how deeply gravity distorts our perception. In ordinary life, light appears straight and predictable. We trust it to illuminate what is real. But around objects with unimaginable mass, such as black holes, gravity is so intense that space itself curves like liquid fabric under the strain. Light is not merely deflected, it is caught in this curve, as if space is quietly whispering, "There's no straight line here anymore." Einstein's theory of general relativity predicted this over a century ago. He showed us that light, though massless, is still bound to the rules of curved space-time. Near a massive star or a black hole, a ray of light might take a path so distorted that it forms a circle. In some cases, it may orbit endlessly, like a moth trapped around an invisible flame. To anyone watching from afar, that light might seem frozen or even returning toward its source. The idea of something as pure as light, something that defines our sense of forward being dragged backward, is a paradox that shatters our intuition. Now imagine standing near such a place. You look up at the stars, and some of them may not even exist anymore. Their light could have bent, ricocheted, and looped so many times that it reaches you centuries after their death. What you see is not the present, but a distorted story, played out in warped echoes. You might even see multiple versions of the same star, a cosmic mirage created by the bending of its light. This paradox forces us to question what seeing even means. If light can bend and return, then how much of the universe is truly visible to us? Are we witnessing reality as it is, or just a reflection of its most deceptive pathways? In this way, light becomes both the storyteller and the trickster, bending back not just on itself, but on our understanding of truth. In the depths of space, stars live lives that seem eternal to us blazing giants that outshine entire galaxies. But beneath their brilliance lies a destiny as strange as it is, terrifying. Some stars do not simply burn out or fade. They collapse inward, devouring their own essence as if they are both predator and prey. This paradox, the star that eats itself, reveals a cosmic truth. Even the mightiest sources of light are not immune to their own hunger. A star's life begins with balance. Gravity pulls its mass inward, while the furious nuclear fusion at its core pushes outward, creating a perfect tension. For millions, even billions of years, this balance is maintained and the star shines steadily. But as it ages, the fuel that powers its light runs out. Hydrogen becomes helium. Helium becomes heavier elements. And soon the star's core is filled with materials it cannot fuse easily. Gravity wins. The star begins to collapse under its own weight, and in doing so, it starts to devour itself. The most extreme version of this process births a black hole, a singularity so dense that even light cannot escape. It's a final act of cosmic cannibalism, where the star's own mass compresses into an infinite point, erasing the very space it once occupied. But before this ultimate transformation, there's a violent death throe. Some stars explode in a supernova, scattering their outer layers across space, even as their core shrinks into a crushing void. Others skip the explosive farewell altogether, folding directly into themselves, as if they are quietly swallowing their existence. This paradox is unsettling because it blurs the line between life and death on a cosmic scale. A star that collapses into a black hole doesn't truly disappear. Its gravity persists, shaping everything around it, bending time and light like a cosmic phantom. In a sense, the star lives on, but in a form that is unrecognizable, a hungry shadow that grows by consuming everything nearby. Consider the philosophical weight of this. A star which once gave life and warmth to planets now becomes an object of destruction, not by external forces, but by its own nature. It burns so brightly that it eventually burns out, collapsing into its own creation. It is both the cause and the victim of its own demise, a paradox of self-consumption that mirrors every cycle of creation and destruction in the universe. To observe such a phenomenon is to witness time itself folding inward. The light from the dying star takes years, sometimes millions of years, to reach us. When we finally see the collapse, it has already happened long ago. It is as though the universe lets us watch a ghost devour its own body. The star that eats itself reminds us that everything in the cosmos is temporary. Even the brightest light will one day turn inward, devouring itself in silence, leaving only gravity, darkness, and echoes of what once was. Gravity, as we know it, is supposed to be the silent pull of matter. It's the force that binds us to the earth, that keeps the planets dancing around the sun, that sculpts galaxies into spirals and clusters. It's comforting, in a way, to think of gravity as a loyal companion to mass. No coal. But the cosmos doesn't play by rules that are always comforting. There are places, forces, and phenomena where gravity seems to appear without any visible mass, and invisible. Sculptor shaping reality from the shadows. This is the paradox of gravity without mass, and it challenges the very foundation of how we understand the universe. We first stumble upon this mystery when looking at galaxies, when astronomers mapped the rotation of stars within these colossal systems. They expected to see something predictable, stars closer to the center spinning fast, while those farther out would slow down, much like planets in our solar system. But instead, they found stars at the edges of galaxies spinning far faster than they should. as if some unseen hand was tugging them outward. There wasn't enough visible matter, no stars, no gas clouds, to explain this extra gravitational pull. Something invisible was there, something exerting gravity without showing itself. We gave it a name, dark matter. Dark matter, by its very definition, is invisible. It doesn't emit light or interact with normal matter in ways we can directly measure, yet makes up most of the universe's mass. It's as if the universe itself is a puppet show, and all the strings are made of a material we can't see. We watch the stars move, the galaxies collide, the cosmic web stretch across billions of light years. But the real actors, the dark scaffolding, remain hidden, and the paradox deepens with dark energy, while dark matter holds things together. Dark energy seems to be pushing the universe apart, accelerating its expansion at a rate no one predicted. It's a force we cannot see, measure, or fully understand, yet it is powerful enough to stretch space itself. How can there be gravity-like effects and cosmic acceleration without visible mass? How can nothing push everything apart? This paradox forces us to admit that our universe might be built on rules far stranger than we've imagined. Gravity might not just be the pull of matter. It could be a property of space itself, something woven into the very fabric of existence. Or perhaps it's a shadow of dimensions we cannot perceive, a whisper from realms that lie beyond the reach of our senses not to think about gravity. Without mass is to question every assumption we make about reality. If invisible matter and energy dominate the cosmos, then what we see, the stars, the galaxies, even the atoms in our bodies might be just the surface of something far deeper. We are living in the glowing skin of a universe whose true body is hidden from view. This is not just science, it's almost poetry. Gravity without mass is the silent reminder that the universe's greatest forces are not always the ones we can see. A black hole is supposed to be the ultimate void, a place where light vanishes, where space and time themselves are dragged into oblivion. It's the cosmic predator we imagine as an endless mouth, swallowing everything that crosses its path. But the more we study these mysterious objects, the less they resemble the simple monsters we once feared. What if the black hole itself is nothing more than a mirage? What if, instead of being a solid thing, it is a shadow cast by warped space-time, a strange illusion born from the way gravity twists our perception of reality? This is the paradox of the black hole mirage. The first illusion lies in the event horizon. From the outside, the event horizon looks like a surface, a boundary beyond which nothing can escape. But this surface isn't a surface at all. It's simply the point where the pull of gravity becomes so overwhelming that even light, the fastest traveler in the universe, cannot return. Nothing is physically there, yet to an outside observer, it appears like a glowing edge, a place where all movement stops. A black hole isn't an object with borders. It's a geometry of no return, an absence masquerading as a shape. Then there's the paradox of time. Near the event horizon, time slows to an almost unbearable crawl. To someone falling into a black hole, the journey might feel quick, almost instant. But to someone watching from a distance, that same fall would look like an endless freeze frame, as if the falling object were suspended forever on the edge of the horizon. The black hole creates not just spatial distortion, but temporal mirages, making now and never collapse into one another. Even its shape isn't what it seems. Black holes are invisible, yet they announce themselves by bending the light from everything behind them. This gravitational lensing creates ghostly rings and arcs, making distant stars appear multiplied, bent, or even reversed. We think we see the black hole, but in reality, we see the absence it creates, the way it distorts everything around it. It's like staring at the curve of a glass and mistaking it for a solid wall. And then there's Hawking radiation, the faint, ghostly glow that might leak from black holes due to quantum effects. If this radiation is real, then black holes aren't eternal prisons. They evaporate over time, slowly dissolving like shadows under a relentless sun. Does this mean they were never things at all? but merely temporary scars in spacetime? The black hole mirage forces us to confront the unsettling possibility that what we see in the universe is never the full truth. We think of black holes as monsters lurking in the dark, but perhaps they are nothing more than mirrors, reflecting the limits of our understanding back at us. They are both real and unreal, dense enough to warp entire galaxies, yet ephemeral. Enough to vanish given enough time. To stare at a black hole is to stare at the universe's greatest trick, a hole that isn't a hole, a darkness that glows and a presence defined by its absence. In the logic of everyday life, shadows are defined by absence. Where there is no light, there is shadow. But in the depths of the cosmos, this simple truth begins to unravel. There are places where shadows don't simply consume light. They emit a strange kind of glow, a brightness born not of illumination, but of destruction. This is the paradox of the shadow that burns bright, a phenomenon that challenges the very meaning of light and darkness. Consider the space around a black hole. By all accounts, it should be the darkest place in the universe, an eternal void. That swallows every photon. And yet, just beyond its event horizon, there is often a violent brilliance, a glowing halo of radiation known as an accretion disk. This is no gentle starlight, it's a blinding fire forged from the agony of matter, being torn apart. As gas, dust, and even entire stars spiral toward their doom, they are compressed, heated, and shredded until they blaze hotter than the cores of suns. What should be the ultimate shadow becomes the brightest beacon in the universe. This paradox isn't limited to black holes. Neutron stars, those ultra-dense remnants of stellar collapse, can spin at staggering speeds, producing beams of radiation so intense they outshine entire galaxies. These remnants are, in essence, the shadows of dead stars, objects that have collapsed beyond the point of normal life. And yet, their death throes ignite a brilliance that defies reason. From the ashes of darkness comes light more radiant than the living star that came before it. There's something deeply symbolic about this paradox. We think of light as the force of life and shadow as the harbinger of death. But here, in the cosmic theater, death itself becomes a source of light. The very act of destruction, the spiraling collapse, the crushing force of gravity creates the conditions for the brightest fires we have ever seen. It is as if the universe is telling us that creation and destruction are not opposites, but partners in an endless dance. To witness this is to realize how fragile our concepts of light and dark truly are. A shadow is no longer just the absence of light. It can become the source of illumination, burning brighter than anything else. It's a reminder that the universe thrives on contradictions. What looks like the end of something, a star, a planet, even light itself, can be the beginning of something far more powerful. Imagine floating near a black hole's accretion disk. You would see matter glowing so intensely that it would sear your vision. Yet, beyond that light lies a darkness, so complete, so absolute, that it devours the very concept of seeing. This juxtaposition is not merely scientific, it is existential. It forces us to confront the idea that our definitions of bright and dark, alive and dead, are only human labels, meaningless when stretched across the scale of the cosmos. The shadow that burns bright is the universe's way of teaching us that opposites are illusions. Darkness gives birth to light, light is born from collapse, and every shadow hides a fire waiting to burn. Time, as we experience it, feels like an arrow, steady, unbroken, always moving forward. We wake, we live, we age, and we die, following a timeline that never folds back on itself. But the universe doesn't necessarily obey this simple rhythm. In the strangest corners of space-time, time itself can twist, loop, and fold like a ribbon caught in the wind. The time loop horizon is the paradox where past, present, and future collide, creating a boundary beyond which the concept of before and after begins to lose all meaning. Black holes once again sit at the center of this mystery. Around their immense gravity wells, space-time is so severely curved that time itself slows. To an outside observer, anything approaching the event horizon seems to freeze, as though trapped in an eternal moment. But for the object falling inward, time continues normally, at least until it is stretched, warped, and twisted beyond recognition. The paradox deepens when we consider what lies just beyond the event horizon. The mathematics of relativity suggests that time and space swap roles. Moving forward becomes moving inward. A second for the falling traveler might be centuries to the observer outside, but the time loop horizon isn't limited to black holes. Certain theories of the universe, particularly those involving closed time-like curves, suggest that under extreme conditions, time can curve back on itself, creating loops where an event can influence its own cause. Imagine walking forward and finding yourself back at the same moment you started. Not metaphorically, but literally, as if the fabric of reality has wrapped you inside a cosmic knot. It's like a mirror reflecting not just your image, but the very moment you exist in. This concept forces us to question everything we believe about cause and effect. If time can loop, then what is the first moment? Can the future shape the past as easily as the past shapes the future? Some physicists believe that quantum mechanics hints at this possibility, that particles can influence each other across time, not just space, creating ripples that defy the notion of linear history. The paradox of the time loop horizon becomes even more mind-bending when we imagine an observer near such a region. From their perspective, they might see events happening multiple times, repeating endlessly like a broken record. They might watch a star explode, collapse, and explode again, each cycle identical yet subtly altered, as though the universe itself is trying to rewrite its own script. Philosophically, this paradox is terrifying and beautiful. It suggests that time might not be the steady river we imagine, but a stormy ocean filled with currents and whirlpools. We could be caught in one right now, endlessly living moments that we mistake for progress. What we call memory could simply be our limited awareness of a loop we can't perceive. Standing on the edge of a time loop horizon would be like staring at infinity, bent into a circle. Every moment would be both the end and the beginning. It's a reality where yesterday, today, and tomorrow hold no meaning. Because all three happen at once, or perhaps forever. The time loop horizon reminds us that time is not a ruler we measure life with, but a wild dimension, one that can stretch, twist, and trap us in ways our minds are barely able to comprehend. When we think of the universe, we often imagine it as a vast explosion that happened somewhere, a single point where everything began, radiating outward like ripples from a stone dropped into water. But the universe defies that intuition. There is no center, no fixed point from which all things spread. Every galaxy, every star, and every atom drifts through a cosmic sea where no single place can claim to be the middle. This is the paradox of the universe without center, a reality so counterintuitive that it forces us to rethink the very nature of space. The Big Bang, often misunderstood, wasn't an explosion that happened in one location. It was an expansion of space itself. Imagine a balloon being inflated. The surface stretches, but there's no single point on the balloon's surface where the expansion began. Every point moves away from every other point, and no single location can be called the center. Our universe, on the largest scales, behaves much like that balloon. From wherever you stand, it looks as if galaxies are rushing away from you. But if you were on a distant galaxy, you see the same thing. Everything would appear to be moving away from you as well. This leads to a startling idea. Every point in the universe is both the center and not the center. We are in the middle of an expansion, but so is every other place. The paradox here is not just geometric, it's philosophical. We as humans are conditioned to find beginnings and centers. We want to point to a location and say, this is where it all started. But the universe gives us no such satisfaction. Adding to this mystery is the fact that space itself is expanding, not just the matter within it. Galaxies aren't flying through a pre-existing void. The void itself is stretching. The distances between galaxies grow not because they are moving through space, but because space itself is growing between them. This means that there's no edge to the universe that we can point to, no central spot we can trace back. On smaller scales, this paradox also affects our perception of time. If there's no central point in space, there's also no absolute now across the universe. Different observers moving through space will experience different flows of time. And what's happening in one galaxy may not line up with what's happening in another. The universe without center leaves us with a strange, humbling truth. We are not at the middle of anything. We are not looking out from a privileged point, but from just another speck in a cosmic expanse that stretches equally in all directions. And yet, this lack of center doesn't make the universe meaningless. If anything, it makes every location equally significant. Everywhere is a kind of center, simply because the universe exists in all directions at once. This paradox reminds us that we are adrift in a structure too vast to fit into our instinctive need for symmetry or boundaries. The universe doesn't need a center to exist. It simply is a boundless, centerless ocean of matter, energy, and mystery. We tend to think of darkness as the absence of light, as emptiness or nothingness. But in the universe, darkness is not merely a void. Sometimes it radiates. Sometimes it is more alive, more powerful, and more luminous than light itself, though not in the way our eyes can perceive. This is the paradox of darkness that shines, the phenomenon where what appears to be nothingness holds a brilliance beyond anything visible, a glow that can only be felt in its effects. One of the most profound examples of this is dark energy. It makes up roughly 68% of the entire cosmos, and yet we cannot see it, cannot touch it, cannot measure it directly. It does not shine, but it drives the expansion of the universe, pushing galaxies apart at an ever-accelerating rate. Dark energy is invisible to us, but its influence is written into the structure of the cosmos, like a ghostly fire burning through the veins of space-time. It's a form of light that doesn't illuminate, but instead stretches existence itself, creating a kind of cosmic radiance that defies ordinary vision. Then there's dark matter, which holds galaxies together like an invisible web. Without this unseen force, the stars we see would not remain in orbit. They would scatter, drifting apart into the void. Though we can't see dark matter, we can see the way it shapes galaxies, the way it bends light through gravitational lensing. When light from distant stars travels toward us, dark matter distorts it, creating arcs and halos, an eerie kind of illumination made from shadow. But darkness shines in other, subtler ways. Consider black holes. These cosmic abysses should be perfect darkness, yet around them, we witness some of the most powerful displays of energy in the universe. Their accretion disks emit light so intense that it can outshine entire galaxies, even though the source is an object that itself emits nothing. The black hole's shadow becomes the center of a violent storm of light. As if darkness is the spark that fuels the brightest fires, there's also the cosmic microwave background, faint afterglow of the Big Bang. To the naked eye, space is black and empty. But when we peer through the right instruments, we see that this darkness carries a soft, omnipresent glow, a whisper of the universe's birth. The cold black sky, which we assume to be nothing, is actually filled with the echo of the first. Light still shining 13.8 billion years later, the paradox of darkness that shines challenges us to rethink our senses. What we call light and dark are just interpretations of energy, of electromagnetic waves, of what our fragile human eyes can detect. In reality, the universe is lit by forces we cannot see, by energies that bend, twist, and shape creation in ways we barely comprehend. Perhaps this paradox is not just about science, but also about perception. Just because something is invisible doesn't mean it isn't real. The greatest forces in the universe, gravity, dark energy, dark matter, cannot be directly seen, yet they determine the fate of stars, galaxies, and even time itself. Darkness, in this sense, is not the absence of light, but a deeper form of radiance, one that operates outside the limits of our vision, standing under a starry sky. We look at the darkness between the stars and think it's empty. Space is alive with energy, particles, and fields, an invisible glow that sustains the cosmos. The darkness that shines is a reminder that reality is not defined by what we see, but by what truly is. Gravity is the oldest force we've known, simple, predictable, and universal. It tells planets how to orbit stars, stars how to cluster into galaxies, and galaxies how to weave themselves into the cosmic web. On the other hand, quantum mechanics is the youngest and strangest child of modern science. A world of uncertainty, probability, and particles flickering in and out of existence. Both theories work perfectly in their own realms, but when we try to bring them together to explain gravity at the smallest quantum scales, everything falls apart. This conflict is the paradox of the quantum gravity gap, a chasm in our understanding that reveals a universe far stranger than we can currently imagine. In everyday life, gravity feels solid. We drop a stone and it falls. We walk on the ground and it holds us up. Einstein elevated this understanding by showing us that gravity is not a force at all, but the warping of space-time caused by mass and energy. Quantum mechanics, however, operates on a completely different set of rules, where particles are waves, and reality itself is smeared across probabilities. When we try to describe gravity in quantum terms, the math doesn't work. Our equations explode into infinities, refusing to give answers that make sense. The paradox arises because we know both theories are right, at least in part. General relativity explains the large-scale structure of the universe, black holes, the bending of light, the movement of galaxies with astonishing precision. Quantum mechanics explains the subatomic world so well that it powers all of modern technology, from computers to lasers. And yet, these two pillars of physics refuse to merge into a single coherent picture. The quantum gravity gap is the dark chasm between them, a riddle we cannot yet solve. Black holes lie at the heart of this paradox. They are both massive and small, curving space-time while compressing matter into scales where quantum effects dominate. What happens inside a black hole's singularity? Our current theories can't agree. Relativity predicts a smooth collapse into infinite density, while quantum mechanics insists that uncertainty and fluctuations must prevent such infinities. This tension leads to mind-bending puzzles like the black hole information paradox, where we struggle to understand if information swallowed by a black hole is lost forever or somehow preserved in ways we can't yet detect. The quantum gravity gap forces us to confront the possibility that our understanding of space and time is incomplete. Perhaps space is not continuous, but built from tiny, indivisible kind of pixelated reality at the smallest scales. Perhaps gravity is not a fundamental force, but an emergent phenomenon, a shadow of something deeper we haven't discovered. String theory, loop quantum gravity, and other speculative ideas all attempt to bridge this gap, but none have been proven. What makes this paradox fascinating is how it humbles us. We've sent probes beyond the solar system, peered billions of years into the past with telescopes, and split atoms into smaller and smaller pieces. Yet, when it comes to understanding how the large and the small connect, we are lost. It's as if the universe has hidden its blueprint behind a locked door, leaving us with clues but no key. The quantum gravity gap is a reminder that the universe isn't finished revealing its secrets. Somewhere in the space between relativity and quantum mechanics lies a truth so profound that it could reshape everything we know about reality itself. We think of nothingness as empty, as the absence of everything, no particles, no energy, no sound, no light. But in the strange laws of quantum physics, nothing is never truly nothing. The void is alive, restless, and capable of creating matter seemingly out of thin air. This is the paradox of the void that creates matter, a riddle where emptiness itself becomes the birthplace of existence. At the quantum level, The vacuum of space is not empty. Instead, it's a bubbling sea of virtual particles constantly appearing and disappearing faster than we can observe. These fleeting particles pop into existence, borrow energy from the universe for a fraction of a second, and vanish. It's as though space is a restless ocean, with tiny waves of reality forming and collapsing endlessly. What we call empty. Space is actually a dynamic stage filled with invisible activity. One of the most astonishing examples of this is the Casimir effect. Place two metal plates extremely close together, and the empty space between them isn't truly empty. Virtual particles that form in the vacuum outside the plates create a slight but measurable force that pushes them together. The vacuum is not a void but a fabric that hums with energy, waiting to be tapped. But the paradox grows when we consider the early universe. According to cosmological theories, everything we see today, billions of galaxies, stars, and planets, may have originated from a quantum fluctuation in an empty vacuum. In other words, the universe might have been born out of nothing. A quantum spark, a ripple in the void, could have inflated into the cosmos we now inhabit. Nothingness, in this sense, is the womb of everything. Hawking radiation also arises. From this paradox, near the edge of a black hole, quantum fluctuations cause particle-antiparticle pairs to appear. Normally, they would annihilate each other. But if one particle falls into the black hole while the other escapes, the escaping particle becomes real, draining energy from the black hole in the process. Here, the empty space near the event horizon creates actual matter and energy. Philosophically, this paradox is unsettling. If matter can emerge from the void, then what does existence even mean? We like to imagine that something must always come from something, that creation requires a cause. But quantum mechanics suggests that reality itself might be self-generating, emerging from fluctuations in a sea of potential. The void is an absence. It's potential energy waiting to become form. Think of it this way. The darkness between stars isn't just empty space. It's a field with structure, with the ability to create. And if this is true on the smallest scales, then perhaps the universe itself is a continuous act of creation, with nothingness and somethingness locked in an eternal cycle. The void that creates matter reminds us that reality is far more dynamic than we imagine. Even the emptiest corner of space may be a cauldron of invisible activity, a silent storm from which entire worlds could be born. Energy is supposed to come from somewhere. A ball rolls because you pushed it. A fire burns because there is fuel. Stars shine because nuclear reactions feed their light. In every part of our everyday experience, energy has a clear source and a chain of cause and effect. But the universe, as always, finds ways to defy our rules. There are places and phenomena where energy seems to appear without any obvious origin, as if reality itself is creating something from nothing. This is the paradox of energy without source. One of the strangest examples of this is vacuum energy. According to quantum field theory, the vacuum of space, what we think of as empty, actually contains energy. Not a little energy, but potentially an infinite amount, if our equations are correct. This energy doesn't come from a star or a planet or any physical source. It simply exists, woven into the structure of space itself. It's as if the universe is humming with a constant background song of energy that has no identifiable composer. Dark energy is another piece of this puzzle. It's the mysterious force that drives the accelerated expansion of the universe. We don't know what it is, only that it appears to be everywhere, stretching space at a faster and faster rate. Where does this energy come from? We can't find an answer. It doesn't seem to come from matter, radiation, or any traditional form of energy. It's simply there, pushing galaxies apart as though space itself is breathing, exhaling energy. Without any fuel dot, then there's the strange world of quantum fluctuations. Particles can appear in empty space, seemingly borrowing energy from nowhere, existing briefly, and vanishing. In quantum mechanics, this doesn't violate any rules because the uncertainty principle allows for such brief bursts of existence. Yet this raises a bigger question. If energy can spontaneously emerge in this way, how do we define the boundary between something and nothing? Perhaps the most profound implication of this paradox lies in the origins of the universe. Cosmologists have proposed that the entire cosmos could have emerged from a quantum vacuum, with its total energy adding up to zero, positive energy in matter and negative energy in gravity, canceling out perfectly. In this view, the universe didn't need a cause or an external source. It simply emerged like a bubble forming in an endless ocean of potential dot energy without source challengers, not just physics, but philosophy. It suggests that reality doesn't need permission to exist, that something can arise spontaneously, unprovoked, unplanned, and uncaused. It forces us to confront the possibility that the rules we take for granted, like every effect must have a cause, are not universal truths, but local approximations of a far stranger cosmic order dot in our daily lives. Energy always feels tied to effort, to a process, to something we can trace back. But in the universe, energy might be as fundamental as space and time, not needing a source because it is the source. The paradox of energy without source reminds us that the universe is not a machine waiting for a key to wind it up. It is a self-sustaining mystery, powered by forces we can barely begin to comprehend. Light is supposed to come from stars, from blazing spheres of fusion that burn across the void. When we see light in the night sky, we instinctively trace it back to its source, a sun, a supernova, or some other celestial engine. But the cosmos is never that simple. There are places in the universe where light appears without a star, where radiance pours from regions that seem empty or dead. These are the starless light wells, a paradoxical phenomenon that makes us question what illumination truly means. Some of the most fascinating examples of this paradox are found around black holes. Black holes themselves emit no light. They are defined by their ability to trap it, yet the regions around them are among the brightest in the universe. The accretion disk of a black hole, made of gas and dust spiraling inward, can blaze millions of times brighter than a galaxy of stars. This light doesn't come from the black hole, but from matter being shredded and heated as it falls into the gravitational abyss. The black hole is starless, yet it shines with a ferocity that dwarfs ordinary starlight. But black holes are not the only culprits. There are interstellar clouds of gas and dust, vast, dark nebulae that sometimes glow without containing a single star. This glow often comes from photons scattered by nearby sources or from the slow release of stored energy, as if the very fabric of the cloud remembers the starlight that once touched it. These regions become ghostly lanterns in space, luminous, without having their own internal flame. Then there are quasars, cosmic lighthouses so powerful that they can outshine entire galaxies, yet they are not stars. A quasar's light comes from material falling into a supermassive black hole at the center of a galaxy. It is a starless well of light, a paradoxical blaze born from destruction rather than creation. This phenomenon challenges our understanding of what light represents. We assume light is the sign of life, of burning fuel, of creation. But in the universe, light can just as easily be the product of decay, collision, and collapse. A region with no stars can still flood the cosmos with radiation, as if the universe is reminding us that brilliance does not require life or even stability. On a philosophical level, the paradox of starless light wells feels haunting. It suggests that light is not a simple property of stars, but of energy itself. It can emerge in the most violent and lifeless corners of reality. A dying galaxy, stripped of its stars, may still glow faintly as its last fragments of matter are consumed and converted into energy. If you were drifting near one of these starless wells, you might feel a strange contradiction. The light would surround you, bathing you in its glow, but there would be no star to point to, no source to anchor your understanding. It would feel like the universe itself was radiating, like the void had decided to burn for no reason other than to remind you of its power. The paradox of starless light wells reveals a simple but unsettling truth. The universe doesn't need stars to shine. It can make light out of destruction, emptiness, or the invisible churn of gravity. In a cosmos like this, even darkness can find ways to glow. We are taught to see matter and thought as opposites. Matter is solid, heavy, and governed by physical laws, while thought is weightless, abstract, and tied to consciousness. But the deeper we peer into the nature of reality, the more this division begins to blur. The paradox of matter turning to thought suggests that, at a fundamental level, the universe may not be built from hard, objective stuff at all. Instead, matter itself could be a kind of information, an expression of something. As intangible as thought, this idea isn't just philosophical. It emerges from the strange principles of quantum mechanics. At the smallest scales, particles don't behave like tiny billiard balls. Instead, they act like clouds of probabilities existing in multiple states at once, only choosing a specific position or form when observed. This means the act of observation, which is linked to consciousness, can shape the outcome of reality. Does this mean that our thoughts influence matter? Not directly in a mystical sense, but the connection between the observer and the observed is far less separable than we once believed. Consider the double-slit experiment, where particles of light or matter behave differently depending on whether they are being observed. When no one watches, they act like waves, existing in many places at once. When observed, they collapse into a single position, as if the universe responds to awareness itself. This is not to say that the mind creates matter, but that matter and the act of knowing it are deeply intertwined, so intertwined that they may be two sides of the same cosmic coin. There is also the idea of information as a fundamental building block of the universe. Some physicists argue that particles, fields, and even space-time itself might emerge from patterns of information bits of data, much like the zeros and ones that power a computer. If true, then matter is not just stuff, but is structured. Form of knowledge, a kind of frozen thought woven into the fabric of reality. Black holes give this paradox another twist. When something falls into a black hole, all of its physical form is destroyed, but the information about what it was, pattern of its existence, might remain encoded on the black hole's surface in a mysterious holographic imprint. This has led to the mind-bending holographic principle, which suggests that the universe itself could be a kind of projection of information stored on a cosmic boundary. If so, matter isn't primary. It's the shadow of information of thought. Philosophically, this raises profound questions about consciousness. If matter and information are interchangeable, could consciousness itself be another form of matter's hidden potential? Is our mind simply the universe becoming aware of itself through its own structures? What we call thought might not be a separate realm at all, but the ultimate expression of matter organizing itself into patterns, complex enough to reflect and imagine. Imagine looking at your own hand. It feels solid, material, unthinking, yet the atoms in your hand are mostly empty space, filled with particles that flicker in and out of existence. Those particles are not fixed things, but probabilities, shaped by interactions and information. In some sense, the hand you see is a form of cosmic memory, matter briefly organizing itself into a shape that can think, reflect, and question its own existence. The paradox of matter turning to thought invites us to see reality as something far less mechanical and far more conscious. Perhaps thought isn't born from matter. Perhaps matter is simply thought, slowed down and crystallized, existing as a pattern that the universe uses to speak to itself. A singularity is supposed to be a point of collapse, a place where space, time, and all known laws of physics break down. It's where everything falls inward, crushed into infinite density. But in one of the greatest paradoxes of the cosmos, a singularity is also where everything expands. According to our best understanding, the entire universe, every galaxy, every star, every atom was once compressed into a singularity, and from that point, it exploded outward in an event we call the Big Bang. How can something defined by collapse also be the source of expansion? This is the paradox of the singularity that expands dot. To understand this paradox, we must first confront the nature of a singularity. In black holes, singularities are hidden behind event horizons, places where gravity is so intense that time and space bend into incomprehensible shapes. In these regions, all matter is thought to collapse into a single, infinitely dense point. It's the ultimate end state, a place where information, energy, and structure vanish into a form we cannot describe. Yet the Big Bang suggests the opposite. From a singularity, not collapse, but creation emerged. The early universe didn't expand into space, it expanded space itself. This is a crucial distinction. Before the Big Bang, there was no outside for the universe to grow into. The singularity wasn't a dot in a void. It was the entire reality compressed into a single state. When it expanded, it didn't move outward like an explosion. It stretched the very fabric of existence, creating both space and time in its wake. The paradox is that a point of infinite density can be both the ultimate prison of matter and the ultimate birthplace of reality. This strange symmetry is mirrored in black holes. Some theories suggest that the singularity at the center of a black hole could give rise to new universes, a kind of cosmic recycling process, where the death of one reality is the birth of another. We can't see past the event horizon to know for sure, but it's possible that our universe itself is the product of such a singularity, a seed from a deeper structure that existed before. Time as we know it. There is also the question of what happens at the end of time. Will the universe continue expanding forever, its galaxies growing more and more distant until it cools into a dark, frozen void? Or will gravity eventually slow the expansion, pulling everything back together into a big crunch, another singularity that could, in turn, explode into a new cycle of creation? The paradox of the singularity that expands suggests that beginnings and endings are not separate, but part of a continuous loop, where collapse and expansion are two sides of the same cosmic rhythm. Philosophically, this paradox challenges our ideas of creation and destruction. We like to think of singularities as dead ends, places where existence stops. But in reality, they might be gateways, points where the universe reshapes itself, where all the old rules are burned away and something entirely new is born. To contemplate this paradox is to realize that our universe may have come from nothing, but not an empty nothing, a dense, singular state where all potential is locked, waiting to unfold. The singularity that expands is the ultimate reminder that even in the tightest confines, existence finds a way to grow. We often imagine space as a flat, endless canvas, a backdrop against which stars, planets, and galaxies exist. But space itself is not static or fixed. It bends, warps, and folds under the influence of gravity, like fabric under weight. In extreme conditions, this folding becomes so intense that space seems to collapse inward, curving in on itself until the very concept of direction loses meaning. This is the paradox of space folding inward, where the very structure of reality becomes tangled and twisted, turning inside out in ways that defy intuition. Einstein's theory of general relativity gave us the first glimpse of this truth. Space and time are not separate, unchanging entities. They form a single fabric spacetime that can be curved by mass and energy. A star, for example, doesn't pull on planets in the traditional sense. Instead, its mass bends space-time, and the planets simply follow those curves. But around extremely dense objects, like neutron stars or black holes, the curvature becomes so extreme that space doesn't just bend, it folds. Paths that once seemed straight collapse into loops. And movement becomes a spiral into the abyss. Black holes are the ultimate example of this phenomenon. At their centers, space and time curve so violently that they effectively invert. Inside the event horizon, moving forward in time means moving deeper inward, toward the singularity. It's as though the directions we take for granted, up, down, forward, back, cease to exist, replaced by a singular direction that all things must follow, inward. But this folding doesn't only happen around black holes. On cosmic scales, space can also be warped by the sheer mass of galaxy clusters, bending light as it passes by. This gravitational lensing creates the illusion of multiple images of the same object, as if space itself is folding and mirroring reality. We see not one universe, but layers of distorted reflections, each a result of space curving inward upon itself. The paradox becomes even stranger when we consider the possibility of wormholes, hypothetical tunnels in spacetime created by extreme folding. A wormhole would connect two distant points in the universe by bending space so dramatically that they touch, like folding a sheet of paper until two distant points meet. If such objects exist, then space is not the rigid stage we imagine, but a malleable fabric that can be twisted into shortcuts, connecting places and times in ways that seem impossible. Philosophically, the idea of space folding inward forces us to question our perception of reality. We navigate the world as if space is uniform and predictable, but this is an illusion born of our limited scale. On cosmic levels, space behaves less like a map and more like a living, breathing structure capable of warping, folding, and even collapsing upon itself. Imagine standing near the edge of a black hole. From your perspective, space might seem to stretch endlessly, but as you move closer, it folds inward so violently that escape becomes impossible. Light itself is trapped by this folding, forced into orbits or swallowed entirely. To an outside observer, you would seem to freeze in time, your image stretched and distorted, while you, in your own frame of reference, would continue moving inward toward a place where space and time are no longer separate or meaningful. The paradox of space, folding inward, is a reminder that the universe is not just vast but dynamic. Space is not a passive container. It is an active player, shaping and reshaping itself under the influence of mass, energy, and time. In our everyday world, echoes belong to sound. A voice bounces off a wall, and we hear it return. But in the cosmos, where the vacuum of space is almost entirely silent, echoes take on an entirely different form. There are no air molecules to carry sound waves across the void, yet the universe is full of echoes, signals, ripples, and imprints of events that happened billions of years ago, still whispering to us without a single sound. This is the paradox of the soundless cosmic echo, where silence speaks louder than noise. One of the most remarkable examples of this paradox is the cosmic microwave background, TM. This faint radiation is the afterglow of the Big Bang, the lingering whisper of the universe's birth stretched across all of space. It is not sound in the traditional sense, but it is a kind of memory of fossilized echo of the moment when the first light broke free. The CMB doesn't roar or hum, yet it tells us about their earliest seconds of existence. It is silence encoded with the story of everything. Gravitational waves are another form of these silent echoes. When massive objects like black holes or neutron stars collide, they send ripples through space-time itself. These ripples are not sound waves, yet they behave like cosmic echoes, carrying the memory of violent, distant events across billions of light years. When we detect them, we are essentially listening to the universe's silent music, a vibration of reality that needs no medium to travel. The paradox deepens when we consider the way light and radiation act as echoes of time. When we look at distant galaxies, we're seeing them not as they are now, but as they were millions or billions of years ago. The light reaching our eyes is an echo of a past that has long since vanished. The universe is, in a sense, a vast hall of silent mirrors where everything we see is delayed, a reflection of what was rather than what is. What makes this paradox fascinating is that these echoes often outlast their sources. A star that exploded a billion years ago is gone, but its echo, its light, its radiation, its gravitational imprint still travels through space, announcing its existence long after its death. Space is filled with these ghostly traces, a silent symphony of events we will never witness directly, philosophically. The soundless cosmic echo forces us to rethink how we understand communication. We equate sound with presence, with the here and now. But the universe communicates in silence. Every photon, every gravitational wave, every faint trace of radiation is a message from a past that still shapes our present. Silence, in this sense, is not emptiness, but memory. Imagine standing alone in space, surrounded by this endless silence. You cannot hear a single sound, yet you are bathed in countless echoes of stars being born, galaxies colliding, and black holes feeding. You are immersed in a quiet roar that spans all of time. The paradox of the soundless cosmic echo reminds us that silence is not the absence of meaning. It is, in fact, the deepest form of connection, a quiet thread that ties us to the birth of the universe itself. We think of dust as insignificant, tiny, fleeting, and easily swept aside. But in the cosmos, dust is far from trivial. A single speck of cosmic dust, smaller than a grain of sand, can carry within it the story of stars, planets, and even life itself. This is the paradox of infinity within dust, the realization that the smallest fragments of matter can hold within them the vastness of the universe. Cosmic dust is not ordinary dirt. It is made of elements forged in the hearts of ancient stars, carbon, silicon, iron, and oxygen, all produced in the nuclear furnaces of stellar cores. When stars die, they scatter these elements across space, where they gather as tiny, drifting grains. These particles, though microscopic, become the building blocks of planets, oceans, and life. Every breath we take and every atom in our bodies was once part of this cosmic dust. In this sense, the infinite history of the cosmos is embedded within the smallest particles. But the paradox deepens when we consider what dust reveals to us. Telescopes often use the glow or absorption of interstellar dust to map the shape of galaxies, nebulae, and star-forming regions. A single particle can obscure the light of distant stars or scatter it, creating patterns of reflection that tell it's about events millions of years old. Dust, though small, can control what we see, hiding some truths and revealing others that benders the mystery of the microscopic universe hidden within these tiny particles. If you were to zoom into a grain of cosmic dust, you'd find an entire landscape, atoms swirling, electrons dancing, quantum fields fluctuating. These infinitesimal worlds operate on principles that defy classical logic, suggesting that even the smallest speck is a universe unto itself. In every fragment of dust, there's a reflection of infinity, the microcosm echoing the macrocosm. Consider a comet traveling through space. Its tail is made of dust and ice, yet within those grains lies the chemical memory of the early solar system, unchanged for billions of years. When this dust falls onto planets, it conceives new worlds with the raw ingredients of life. Something so small that we cannot see it with the naked eye contains the potential to create oceans, forests, and civilizations. Philosophically, the paradox of infinity within dust is humbling. We often look to grand galaxies and colossal phenomena to find meaning, but the universe reminds us that the same complexity lies within the tiniest structures. Dust is both the beginning and the end. It is what stars are born from and what they return to. We too are part of this cycle. When we die, the elements of our bodies will scatter into dust, ready to form new stars, planets, or perhaps beings. But we'll wonder about their origins just as we do now. Infinity. Within dust is the ultimate contradiction. The universe is immensity compressed into a particle. It could rest unnoticed on your fingertip, carrying within it the echoes of eternity. In the strange world of quantum mechanics, particles do not behave like tiny, solid objects. They exist in states that defy our logic, behaving as if they are both many things and no thing at all. Among the most baffling of these behaviors is the paradox of a particle with two lives, a single entity that appears to exist in two different states, two different places, or even two different realities at the same time. This paradox is best illustrated by the phenomenon of superposition. In quantum mechanics, particles like electrons or photons can exist in multiple states simultaneously. Imagine a spinning coin. In the classical world, it's either heads or tails. But in the quantum world, the particle is both heads and tails. at the same time existing in a state of bothness until it is observed. Only when measured does it choose one state. This means the simple act of looking at a particle seems to determine its reality. The famous double-slit experiment reveals this in shocking clarity. When particles are sent through two slits toward a screen, they act like waves, creating interference. Patterns as if each particle passed through both slits at once. But when we try to observe which slit the particle passes through, the interference pattern vanishes, and the particle behaves as though it only went through one slit. It's as if the particle lives two lives, one as a wave, one as a particle, and our observation collapses those possibilities into a single outcome. But this paradox doesn't stop there. Quantum entanglement suggests that particles can share their states with other particles, no matter how far apart they are. If you measure one, you instantly affect the state of the other, as though they are linked beyond space and time. A particle with two lives might not just be living in two places, it might be sharing its life with something light years away, defying any classical notion of separation. Philosophically, the paradox of a particle with two lives challenges our very idea of reality. Are particles inherently real before we observe them, or do they exist as mere probabilities, becoming real only when they are measured? It raises the unsettling question of whether the universe exists in a definite state when no one is looking. There's also the implication that our reality may be fundamentally non-local, that everything is connected in ways we cannot perceive. A single particle could be both here and there, both now and later, both alive and dead, just as Schrodinger's famous thought experiment with the cat suggested. Imagine holding a single particle in your hand, knowing that its life is split across multiple states, multiple paths. What does that say about us? If the building blocks of reality can exist in such duality, perhaps our perception of a singular, linear life is just a projection, a collapsed version of something far larger, something that holds infinite possibilities. The particle with two lives reminds us that reality is not as straightforward as it appears. It is layered, uncertain, and woven from possibilities that coexist until they are forced to reveal themselves. Fire is the ultimate symbol of heat, energy, and movement. It burns, consumes, and transforms everything it touches. Yet, in the cold vastness of the cosmos, there are forms of fire so extreme that they don't just burn, they freeze space and time around them. This is the paradox of fire that freezes space, a phenomenon where energy and heat reach such unimaginable levels that they create stillness instead of motion. To understand this paradox, we need to look at black holes again, those gravitational furnaces that trap even light. Around a black hole, the accretion disk blazes with temperatures hotter than the core of any star, creating the illusion of cosmic fire. Gas and dust spiral inward, compressing and heating until they emit deadly radiation. Yet beyond the event horizon, all that fire, all that motion comes to a halt. From an outside observer's point of view, anything falling into a black hole slows down, appearing to freeze as time itself stretches toward infinity. This strange interplay between heat and stillness is not limited to black holes. Neutron stars, for example, are born in the explosive violence of supernova. Their surfaces can burn at millions of degrees, yet their gravitational fields warp space so strongly that movement around them becomes distorted. In their presence, time slows. Second-near neutron star may not match a second far away. This means that while their surfaces blaze with unimaginable energy, they also create zones where time and space are frozen relative to the wider universe. The paradox grows even stranger when we look at the cosmic microwave background, the faint heat left over from the Big Bang. This fire from the birth of the universe has cooled to just a few degrees above absolute zero, spread thinly across the cosmos. It is everywhere, bathing all of space, but it is so evenly distributed and so faint that it gives an impression of cosmic stillness. The fire that began as the most violent explosion in history now manifests as a whisper of heat frozen across time. Even on a quantum level, energy can behave in contradictory ways. High energy environments, where particles collide at near light speeds, can create conditions that mimic stillness zones where energy is trapped, unable to escape, forming exotic states of matter. It's as though the universe uses extreme energy not only to create chaos, but also to forge moments of absolute pause. Philosophically, the fire that freezes space challenges our understanding of opposites. Heat and motion are supposed to be linked. Where there is fire, there is movement. But in the cosmic theater, the most violent forces can create a kind of frozen eternity. A stillness born not from lack of energy, but from an overwhelming abundance. Of it, doubt imagine standing at the edge of a black hole's accretion disk. The heat would be beyond comprehension, yet as you looked closer, the matter falling into the event horizon would seem to slow, freeze, and stretch like a ghost caught in time. It is the ultimate contradiction, the hottest fire producing the coldest stillness. This paradox is a reminder that the universe's extremes don't fit neatly into our understanding. Fire can freeze, time can stop, and energy can become its own prison. In the reality where opposites can merge, even the simplest, concepts like heat and cold, motion and stillness begin to lose meaning. An orbit, by definition, is movement. We imagine planets endlessly circling stars, moons tracing paths around planets, and entire galaxies rotating like giant wheels in space. Orbit is the dance of gravity and momentum, a delicate balance between falling and moving forward. But in some corners of the universe, this logic fails. There are orbits that appear motionless, where time slows to such an extent that movement seems to stop altogether. This is the paradox of orbit without motion, where the act of orbiting becomes frozen in time. This phenomenon is most famously tied to black holes. Around a black hole lies a strange region known as the photon sphere, where light itself can orbit in a perfect loop. Photons, moving at the speed of light, trace endless circles around the black hole's event horizon, caught in a gravitational trap. From a distance, these orbits look like motionless rings of light eternal halos, neither falling inward nor escaping outward. The photons are moving at unimaginable speeds, yet to an outside observer, this motion is locked in place, a static display of energy frozen in time. Time dilation near massive objects creates another layer of this paradox. According to general relativity, time flows differently depending on gravity. Near a black hole or neutron star, time slows relative to regions farther away. An object orbiting close to the event horizon might complete millions of rotations in its own frame of reference, but to a distant observer, its motion would appear slowed, perhaps even frozen. It's as if orbit, which is inherently dynamic, becomes a moment stretched into eternity. We also see echoes of this paradox in gravitational lensing. When light from a distant star passes near a massive galaxy, the path of that light curves as though it were orbiting the galaxy's gravity. But this orbit is not motion in the traditional sense. It's a bending of space itself. A trajectory so warped that light's forward journey looks like a looping pause, frozen into a ring called an Einstein ring. The paradox becomes more philosophical when we consider what motion really means. Motion requires time without time. There's no change, no forward progress. If time itself can slow or stretch near strong gravitational fields, then motion, as we understand it, can lose all meaning. An orbit without motion is not truly an orbit at all, but a reflection of how space-time can trap even the idea of movement. Imagine observing a spacecraft caught near a black hole's event horizon. To its crew, the ship is moving, orbiting, perhaps even accelerating. But to you, watching from afar, it would seem to crawl slower and slower until it appears frozen at the edge of the abyss. In reality, both views are correct. The motion both exists and does not exist. Depending on your perspective, this paradox is a reminder that the universe is not built to match human intuition. Orbit, time, and motion are not absolutes. They are relative, shaped by the fabric of space-time itself. In some places, the dance of gravity and motion slows to a whisper, creating the illusion of stillness even as reality spins in ways we can't comprehend. We like to imagine the universe as a place of patterns and harmony. Galaxies form beautiful spirals, planets follow precise orbits, and the laws of physics seem unshakable. On the surface, everything appears orderly, predictable, and rational. But look closer, and this order begins to unravel. Beneath the smooth patterns lies chaos, an unpredictable, turbulent undercurrent that quietly shapes everything we see. This is the paradox of chaos hidden in order, where the universe's elegance is built on foundations of randomness and disorder. One of the clearest examples of this paradox can be found in the behavior of stars and galaxies. A galaxy may look like a perfect whirl of stars, but the movements of those stars are chaotic when observed individually. Their paths are influenced by countless gravitational tugs from nearby stars, clouds of gas, and invisible dark matter. What appears as a smooth spiral from afar is up close a swirling storm of unpredictable motion. The same principle applies to weather systems here on Earth. The global climate follows certain predictable patterns, but the path of a single storm or cloud is chaotic, sensitive to the tiniest changes. This is the essence of chaos theory, the idea that small differences in initial conditions can lead to vastly different outcomes. The universe, it seems, thrives on this delicate balance. Between predictable order and chaotic freedom, quantum mechanics adds yet another layer to this paradox. At the quantum level, particles behave in ways that are fundamentally unpredictable. Their exact position and momentum cannot be known simultaneously, a principle known as the Heisenberg uncertainty principle. Yet, out of this quantum chaos emerges the structured world we see. Atoms, molecules, stars, and galaxies all arise from a foundation of uncertainty. The chaos at the smallest scales gives rise to the order we depend on at the largest. Even in biological systems, chaos hides in plain sight. Our bodies are built from molecules that constantly vibrate, collide, and fluctuate, yet together they form the stable structure of life. The human heartbeat, often seen as a symbol of regular rhythm, is actually laced with chaotic fluctuations that make it adaptable and resilient. Without that hidden chaos, life itself would not be possible. Philosophically, chaos hidden in order challenges our assumptions about control and predictability. We like to believe that the universe operates according to rules we can master. But this paradox shows that unpredictability is not a flaw, it's the foundation of everything. Without chaos, stars would not form, planets would not evolve, and life would never emerge. Imagine looking at a calm night sky. The constellations appear fixed, eternal, and unchanging. Yet every star in that sky is moving, colliding, and transforming in ways we cannot predict on human timescales. The order we see is just a snapshot of deeper, hidden chaos at work. Paradox teaches us that order is not the absence of chaos, but its mask. The universe is both structured and wild, balanced and unpredictable. Chaos is not the enemy of order, it is its secret architect. Collapse in our understanding means an ending, a fall, a failure, or a complete breakdown. When something collapses, we assume it's dead, gone, or reduced to nothing. But in the universe, collapse is rarely final. Instead, it is often the beginning of something new. This is the paradox of deathless cosmic collapse, when destruction becomes creation, and endings become doorways to entirely new realities. The life cycle of stars is the clearest example of this paradox. When a massive star exhausts its fuel, gravity takes over. The outward pressure that kept the star stable vanishes, and the star collapses inward under its own weight. We might expect this to be its death, but what emerges from that collapse? A supernova explosion, brighter than an entire galaxy, scattering heavy elements like carbon and iron across space. These elements born from the collapse of a star are the building blocks of planets, oceans, and life. The death of the star becomes the birth of everything else. Black holes represent an even stranger form of this paradox. When a star collapses far enough, its core compresses into a singularity, an object of infinite density where the known laws of physics break down. From the outside, this appears to be the ultimate death, a gravitational tomb from which nothing can escape. Yet black holes are far from dead. They shape galaxies, devour matter, and emit powerful jets of radiation. Some theories suggest they could even spawn new universes beyond their event horizons, a cosmic rebirth born from collapse. On a larger scale, entire galaxies collide and merge. What appears at first glance to be destruction, a chaotic smashing of billions of stars. In reality, the formation of something new. Stars are rarely destroyed in these collisions. Instead, their gravitational dances trigger new waves of star formation. The collapse of one structure leads to the flourishing of another. Even the universe itself may follow this pattern. Some cosmologists believe the universe could one day end not with a whimper, but with a collapse, a big crunch, where all matter is drawn back together. But could that collapse be the beginning of another Big Bang? Could our universe be one? In an infinite series of expansions and collapses, each deathless, each carrying forward the echoes of the last. This paradox forces us to question the nature of endings. In human terms, we see collapse as failure, as the point where everything stops. But the cosmos tells a different story. Collapse is not always a final act, but part of a larger cycle. Stars collapse to give life to planets. Galaxies collapse to create new structures. Even black holes, the ultimate symbols of cosmic doom, may slowly evaporate through Hawking radiation, returning their energy to the universe. Philosophically, deathless cosmic collapse is a lesson in transformation. It suggests that nothing in the universe truly dies, it only changes form. We, too, are part of this cycle. The atoms in our bodies were born in the heart of collapsing stars. One day, those atoms will scatter again, perhaps to form another world, another life, another consciousness. Imagine standing at the site of a supernova, watching a star rip itself apart. To human eyes, it looks like violent death. But to the universe, it is simply renewal, a necessary step in the creation of everything else. The paradox of deathless cosmic collapse teaches us that endings are illusions. What we call collapse is, in truth, the universe's way of reinventing itself again and again without ever truly ceasing to exist. We usually think of nothingness as an empty, unchanging void, an absolute absence of anything that could grow, shrink, or transform. But in the cosmos, nothingness itself expands. Space, which we often mistake for a background, is alive, with growth stretching wider and wider as the universe ages. This is the paradox of nothingness growing larger. The realization that emptiness is not static but dynamic, swelling like a living organism even as it remains nothing. The most striking example of this paradox is the expansion of the universe itself. Since the Big Bang, space has been stretching, not just moving galaxies apart, but creating more nothingness between them. The galaxies are not flying through a pre-existing void. The void itself is expanding as if the fabric of reality were being woven on a cosmic loom. This expansion isn't slowing down either. Observations show that the rate of expansion is accelerating, driven by the mysterious force of dark energy. In other words, emptiness isn't just growing, it's growing faster and faster. This challenges our very concept of space. If we imagine space is a stage where matter and energy play out their interactions, then the stage itself is getting bigger without any effort from the actors. Space creates more of itself without needing to come from anywhere. This feels impossible. How can nothing increase in quantity? Yet this is exactly what is happening. Every second, more empty space appears between galaxies, carrying them farther apart. The paradox deepens when we look at the role of quantum fluctuations. Even in what we think of as true vacuum, space is never completely empty. It seethes with virtual particles popping in and out of existence. As the universe expands, the total amount of this vacuum energy grows. meaning that nothingness itself holds the seeds of something. Far from being static, emptiness has the power to shape the fate of the entire cosmos. If we project this process into the far future, the consequences are staggering. If expansion continues indefinitely, galaxies will drift so far apart that they will no longer be visible to each other. Eventually, only empty, dark space will dominate, a universe of growing nothingness. And yet, this emptiness will not be dead. Dark energy will continue to push, stretching the void into an ever larger nothing that fills everything. Philosophically, this paradox forces us to question the meaning of nothing. Is there truly such a thing as absolute emptiness? Or space itself a kind of entity with its own properties, its own capacity to grow and evolve? If nothingness can expand, does that mean it is something after all? Imagine standing on Earth and looking at the night sky. The stars and galaxies you see are already far away, but the space between them is growing. That blackness you think of as empty is swelling silently, invisibly, reshaping the entire structure of the cosmos. You are not just looking at emptiness, you are looking at something that is growing, even as it hides its nature behind the mask of nothingness. The paradox of nothingness growing. Larger reminds us that even what we call nothing may hold infinite mysteries. Emptiness, it seems, is not the absence of reality, but its most dynamic and expansive form. A horizon is supposed to be a boundary, an edge we can see but not reach, a simple line separating what is near from what is far. On Earth, it's the distant curve of land or sea. But in the universe, horizons are not mere lines. They are boundaries of reality itself, places where what we know and experience begins to break apart. The paradox of the horizon beyond reality emerges when we realize that certain cosmic horizons are not just visual limits, but walls of physics thresholds beyond which time, space, and even truth as we know it cease to behave in ways we can understand. The event horizon of a black hole is the clearest example. This is not a surface or a physical object, but a boundary of no return. Anything crossing it, light, matter, even information, is forever lost to the outside universe. To an observer far away, anything approaching the event horizon appears to slow, stretch, and freeze as if time itself were clinging to the edge. To the object falling in, however, time moves normally, and the crossing is uneventful. Two realities exist at once, one frozen on the horizon, one plunging inward. The horizon becomes not just a visual limit, but a place where reality splits into contradictory truths. The universe itself has a horizon, an edge beyond which we cannot see. Because the universe is expanding faster than light can travel, there are regions of space that will forever remain beyond our observational reach. Light from those places will never reach us. This cosmic horizon defines the limits of what we can know, but what lies beyond it? Are there galaxies, stars, or even entirely different laws of physics? We may never find out. The horizon beyond reality is not just about distance, it is about the limits of knowledge itself. Even in quantum physics, horizons emerge in unexpected ways. The Unruh effect, for example, suggests that an accelerating observer will perceive a warm horizon of radiation, even in a vacuum. This horizon is not a physical object, but a boundary created by perspective where one observer sees nothing. Another sees a field of energy. Reality itself seems to depend on where you stand, philosophically. The horizon beyond reality is a profound metaphor. We live our lives with a sense of certainty, believing we understand the world around us. But just beyond our mental horizons, there are truths we cannot reach, ideas, dimensions, and realities that remain hidden. What we call reality might just be the small, visible patch of a far larger and stranger landscape. Imagine standing near a black hole, looking at its event horizon. It appears like a silent, perfect circle, a gateway to nowhere. Yet beyond it lies a region you will never know, a place where even time is warped beyond recognition. To cross that horizon is to leave not just this universe, but the very framework of what we call reality. The paradox of the horizon beyond reality teaches us that boundaries are not always where things end. They are often where the most profound mysteries begin. Light is the fastest thing we know. It races through the cosmos at 299,792 kilometers per second, a constant speed that defines the very structure of space and time. We think of it as a messenger of the universe, forever in motion, carrying the stories of stars and galaxies across unimaginable distances. Yet, in certain extreme conditions, light can appear to stop. It can hover, trapped in place, as though frozen between moments. This is the paradox of light that stays still, a phenomenon that challenges the very idea of motion and speed in our universe. The event horizon of a black hole is the most striking example of this paradox. To an outside observer, any beam, light aimed outward from the edge of a black hole will never escape. Instead, it appears to hang there, frozen in time, as if the black hole has stolen its motion. From the perspective of someone watching, the light seems locked in place, unable to move forward. Yet, for the light itself, time does not pass in the way we understand. It's not that it stops moving, it's that the warping of space-time around the black hole makes its journey unreachable to anyone looking in. There are other ways light can be slowed or seemingly frozen. In advanced laboratory experiments on Earth, scientists have managed to slow light to a crawl, reducing its speed to a few meters per second by passing it through special states of matter called Bose-Einstein condensates. In some cases, they've even stopped light entirely, holding it in place like a photograph trapped in midair, only to release it later. These experiments reveal that light is not always untouchable or constant. It can be manipulated in ways that make it feel almost solid. Gravitational lensing offers another strange twist to this paradox. When light from distant galaxies bends around massive objects, it can form loops and rings, appearing to hover in place. It's still moving, of course, but from our perspective, its path seems to hold steady, frozen in an eternal frame. What we see might be light that has been traveling for billions of years, caught in gravitational curves so extreme that it creates an image that never changes. Philosophically, the idea of light standing still challenges our perception of time itself. Light defines how we measure time, our clocks, our distances, even the way we understand now is tied to its speed. If light can appear to stop, does time stop with it? Are we seeing a moment preserved forever, like a cosmic memory that never fades? Imagine standing at the edge of a black hole, watching a photon hover near the event horizon. It's not moving forward in your view, but from its own perspective, it's still traveling at light speed, caught in a warping of space. And time so intense that your eyes can no longer make sense of it. That single photon could remain there, frozen in your vision, long after everything else around you changes. The paradox of light. That stays still is a reminder that even the fastest and most fundamental aspects of our universe can be twisted by the cosmic fabric they inhabit. Light, which defines movement, can become a symbol of stillness, a contradiction that makes the universe even more mysterious. The universe is not a simple stage of stars and empty space. It is an endless spiral of phenomena that defy our logic, twist our definitions, and push the limits of what we can even call real. From light that bends back on itself, to shadows that burn bright, from singularities that both collapse and create, to horizons that split truth into two versions of reality, every paradox. We have explored whispers the same unsettling truth. The universe is not here to be understood. It is here to be experienced, questioned, and marveled at as we journeyed through these 25 paradoxes. We've seen that the universe is neither purely ordered nor purely chaotic. It is both at once an infinite dance between creation and destruction, light and shadow, time and eternity. Stars are born from dust, only to collapse into black holes that may, in turn, give birth to new worlds. Time flows forward, yet slows, stretches, and loops, as if mocking the very concept of before and after. Even nothingness, which we assume to be empty, expands and grows, carrying with it the seeds of everything that will ever exist. Perhaps the greatest paradox of all is that we fragile beings of carbon and memory can look up at this vast, unknowable cosmos and even begin to comprehend a fraction of its mysteries. Our minds, tiny sparks of consciousness, are capable of questioning the nature of light, space, and time, even though we are built from the very stardust that these paradoxes describe. We are part of the puzzle trying to solve itself, like a thought wondering where it began. And yet, for all our theories and instruments, we remain surrounded by a mystery. Science gives us glimpses, models, and equations. But beyond them lies a horizon beyond reality, a place where our understanding ends. Maybe that's the beauty of the cosmos, not that it can be fully explained, but that it forever invites us to explore dots. So, as we close this journey, remember, the universe doesn't need to make sense to be real. Its paradoxes are not flaws, but signatures of its depth, proof that existence is far stranger and far more profound than we can ever imagine. In the silence of the night sky, as you look up, you are not just seeing stars, you are staring into the infinite questions that will always remain unanswered.